Okay, we're gonna get started. Welcome back. Hope you had a good break. We're gonna pick up with chapter 15, which we're almost finished with. We have one more topic to discuss, and let's discuss that. Yeah. So last time we hit pretty much the KSP topic, and again, KSP, as we talked about, is the solubility uh, product, and it's the equilibrium constant for things that are insoluble, typically based on solubility rules. So they typically will always have the similar sort of setup here. Silver chloride, for example, going to silver ion and chloride ion in this case. And that's usually how most of these are written. Solid on the left are sort of aqueous ions on the right. And that means when you do write the sort of KSP expression, it typically is just the products, as the reactants are usually solids. And we end up with something that looks like this. We talked a lot about a few different things that affect solubility. We talked about the effect of a common ion. Again, the effect of a common ion is it will really keep the salt together and really lower its solubility. And that's, again, Le Chatelier's principle. The only place where you have ions are on the right-hand side. So if you have a common ion, it's going to cause the equilibrium to shift to the left, and it's going to keep it together. And that's what we saw through calculation and also just in general talking. Other things that affect solubility are things like pH. So if you have an insoluble base or an insoluble acid, they will become more soluble in either an acid or base, depending on which one you have. And that also has a lot to do with, for example, I think we maybe looked at magnesium hydroxide. And again, that's going to make magnesium and a couple of hydroxides here. So if you have this, which is obviously a base, you added acid to it. That's going to be a supply of H plus. Those guys are then going to come together and make water. That essentially is going to remove hydroxide from the equilibrium, going to cause the equilibrium to shift to the right, and thus it will dissolve more in that sort of solution. Similar sort of effect if you have an acid and you add a base, you'll make water and kind of shift it to the ion side. The sort of one of the last things we talked about that sort of affects solubility is concentration. And the concentration of the ions present in the solution does make a big difference as to whether or not you actually see a solid form or not. That is where we calculated Q, which is calculated the same as the KSP. So you can calculate something like Q and compare it to the KSP to determine whether or not a solid would form. If Q is greater than the KSP, then we would expect a solid to form, as it should shift this way, and we would expect to precipitate. If Q is less than the KSP, we would expect no precipitate, as it should shift to the right. And obviously, if Q equals KSP, then you're pretty much at that point where you will see a solid start to develop pretty soon, since it is going to be a saturated solution at that point. A couple other things that we talked about of advantage of KSP is you can use the KSP and knowledge of the KSP to selectively precipitate out ions from solution, as we talked about, and as we do in the qualitative analysis experiments. We did an example there where we wanted to precipitate out the bromine ion and leave the chloride still floating around, and we figured out using KSP as to what concentration of silver we would need to do that. Any questions on any of that stuff there? If you remember any of that stuff. All right, then we're off to the last part here of chapter 15. And we're going to talk about another equilibrium, which is complex ions. And a complex ion is essentially a metal ion, usually in the center. And then it usually has one or more molecules or ions attached to it. These molecules or ions are what are known as ligands, and ligands are weak bases. And if you ligands are not weak bases, sorry, ligands are Lewis bases. And if you remember the definition of a Lewis base that we talked about, A Lewis base is something that will donate a pair of electrons. So typically things that are good Lewis bases are things that are polar and have non-bonding electrons. Things with a negative charge means they have extra electrons to donate. So for example here, the cobalt here will add on our chloride. Chloride here is our ligand in this case. And we will get this complex ion that will form. And essentially we have cobalt in the middle. And we got 4 of these chlorides attached to it. Cobalt in the middle has a +2 charge. And because it has a positive charge, it is electron deficient, which actually makes it a good Lewis acid, something that's able to accept electrons because it has that positive charge. The chloride here is donating its electrons over or transferring its electrons over. We can actually write an equilibrium expression for this, and to add to our ever-growing list of Ks, this is what is known as the Kf, or the formation constant. It is the equilibrium constant for complex ions. So this is the equilibrium constant for complex ions. It is no different than any other equilibrium constant, and obviously we write it the same way, the expression. We take products over reactants, still use our coefficients. So like KSP is for things that are insoluble, KF is specifically sort of the equilibrium constant for complex ions, just like, Ka is for weak acids, Kb is for weak bases, and so forth along the way. Now, the relationship here is as the Kf value increases, the stability of that complex ion also increases. And it's really the same basic equilibrium idea. If we have a large value of K, that means we should mainly have products. And if I mainly have products, that means I mainly have my complex ion over here. Yeah. And I'm going to have that nice and stabilized. So when we talk about sort of these ligands, by the way, they actually do come on one at a time. So they don't actually come on, for example, like what we see here in this equation. They don't all 4 just hop on at the same time. It's actually a stepwise fashion. And what we're looking at here is actually the overall sort of reaction that takes place. So what actually happens in this particular case along the way to kind of put on all of those ligands onto that metal is the very first thing that would happen is the metal would actually just pick up one of those ligands. So we'll have some cobalt, it will pick up a chloride, it will set up a little equilibrium, we'll get COCl plus. And believe it or not, there is sort of a K value associated with just that little process there of doing that. The next thing that happens is this guy that's already picked up one of those ligands will then pick up another. And we will end up with COCl2, also an equilibrium sort of expression for that. And then this guy will continue on. So it's very similar to how acids, for example, lose hydrogens one by one. These guys sort of gain their ligands also one by one. So next step would be we would put on the next chloride, end up with COCl3 minus, also an equilibrium. And lastly, our COCl3 minus will pick up the last chloride and end up with the complex ion that we see there in the book there. And we'll end up with that and a K4 in this case. And these are all equilibrium sort of steps as we continuously kind of individually put these on. And just like any others, what we actually see here is really the overall reaction that is happening. And if we added all these guys together, this guy and this guy would cancel, this guy and this guy would cancel, this guy and this guy would cancel, and we would be left with the overall reaction, which is basically overall this cobalt picked up 1, 2, 3, and 4 chlorides and basically made this complex ion here. And if we wanted the Kf value for this and we happen to have known all these individuals, when we add these type of equations together, what do we do with the K values? We multiply them, yeah? So we don't add them. So you can multiply basically K1 times K2 times K3 times K4. And that technically is how you could get the Kf value if you knew each individual step along the way. And I show you this because sometimes with these type of problems, you're just looking at maybe the overall reaction. Sometimes in these type of problems, they will give it to you kind of in a stepwise fashion, each of these sort of steps along the way. So you could always, if you have it in sort of a stepwise fashion, you could add them together, get the overall reaction, and also figure out what the overall K value is for that. Any questions on that there? Okay. Now, as I mentioned before, ligands, which are Lewis bases, some good and common ligands are water. And as I mentioned before, something that is polar has got some non-bonding electrons like water. It's a very good Lewis base. Something like ammonia as well is polar. It's got those non-bonding electrons. As we just saw there, chloride gained some electrons, so it's negatively charged. So again, these make really good sort of ligands. Again, as I mentioned, a lot of times with complex ion, the metal is really acting as sort of the Lewis acid as it has a positive charge, and again, kind of electron deficient, being able to do that. Another sort of number that we sometimes refer to when we're talking about complex ions is what's known as coordination number, and we'll talk more about it when we get into complex ions in a later chapter, a little bit more detail. But the coordination number is actually the number of atoms that are directly attached to the metal in a complex ion. So, for example, if we had our cobalt on the last example, where we have our chloride, basically the coordination number here is going to be 4, as it has 4 chlorides directly attached to the metal in the complex ion. If our cobalt was there, each of the waters would attach actually to the metal through its oxygen, because oxygen is more negative on water, and that's going to be attracted to the positive metal in this case. And if we look at this here, maybe squeeze them all in, try one more here, and spot right about there. And we look at the 6 waters sort of attached. Each are attached through the oxygen. 1, 2, 3, 4, 5, and 6. So again, this has a coordination number 6. Now, sometimes people get into a habit when they look at complex ions, they just go, well, isn't the coordination number pretty much just this number down here? And the answer is sometimes it is, and sometimes it's not. And it actually depends on the ligand that is there. And each of these ligands that are up here in these pictures, or even up here, these are all what are referred to as being monodentate. And what that basically means is for each of those ligands, they will only attach to the metal through one atom. Now, there are some ligands that can actually attach to the metal in a complex ion through multiple places. Our friend oxalate, for example, is what is referred to as being bidentate. And what that basically means is you get a 2-for-1 deal with oxalate. So if you had a metal and you had oxalate and you drew oxalate, it looks something like this, perhaps. And each molecule of oxalate can actually attach to this oxygen and that oxygen as well. And if you had, for example, 2 of these guys, this guy could also attach in 2 places. So if you had a formula for this, let's just say this was like cobalt or something. Put a cobalt in there. Your formula would look something like this: cobalt C2O4 and a little 2 down there. And in that case, it would probably be like a -2 left over. And when you look here, you might think the coordination number is 2, but in this particular case, it is 1, 2, 3, and 4. The coordination number would actually be 4 in this case. So as we'll learn in a later chapter, we can go a little bit more into complex ions. Not all ligands are the same in the sense of how they bind to the metal. Some have the ability to bind in multiple places, and that affects sometimes the coordination number. But if you have something that only binds in one place that's monodentate, like water, ammonia, chloride, and those guys, basically however many there are is what the coordination number would be. Any questions on that there? All right, so let's take a look at a problem here together so we could talk about some of the differences that we do in these type of problems that maybe we don't do in other problems. And in this particular case, we're going to take 0.2 moles of copper 2 sulfate, and we're going to mix it with a liter of 1.2 molar ammonia. And we want to know what is the concentration of free copper 2 at equilibrium. And obviously, we have our Kf value given to us in this particular case. So a couple of things we're going to do with this, and just for this problem, we're going to assume that the total volume for everybody is 1 liter, and it stays at 1 liter basically. So what we're going to do is we could write our Kf expression in this case, and our Kf would be, again, our products divided by our reactants. And again, we want to make sure we don't forget to take that NH3 to the fourth. NH3 to the fourth. And that's going to equal our 5 times 10 to the 13 in this case. And again, that's a 3. So we're going to get the initial concentration of the copper, and the initial concentration of the copper is going to come from our copper 2 sulfate here. And again, since we're keeping everything at 1 liter, basically we got 0.2 moles over 1 liter will give us a concentration of 0.2 molar for our copper. So initially here we will do an ice table, and we'll use our initial concentration here of our copper. Obviously in this case here, our only source of ammonia obviously is ammonia. And we're going to keep everything at 1 liter. So that is going to be the concentration here, 1.2 molar. And we're going to go with 0. So the first sort of difference that we do with these type of problems that we haven't done in past sort of ice tables is this. It has to do with our Kf value. And if we look at our Kf value, is it a small value or a large value? This is a large value, right? And typically Kf values are really large values. This is large value, but there are some that are even larger than this. And because it definitely is a large value of K, we do make an assumption here. And the assumption is we do assume that this reaction is going to pretty much kind of fully go to the right-hand side because it's pretty big. We're going to essentially have all products in this case. And because on the product side, we have our complex ion, which is a metal in the middle and ligands on the outside, we end up also assuming that because it's going to the right, we're going to make this complex ion that our metal will be like our limiting reagent. It is going to get completely used up because you can't really make a complex ion if you have no more metal, right? So in order to make the complex ion, we need the metal in the middle, and it's going to be like our sort of limiting reagent. So when we do these type of problems, that is one of the assumptions that we make. And what that means is we actually will know the change that's going to occur. So normally when we do molarity in an ice table, we use X's and stuff like that. But in this particular case, because we're making this assumption, we actually know what the change is going to be. And the change is going to be basically our copper. And that means when we get to the change, this is going to be minus 0.2. This will be minus 4 times 0.2. And this will be plus 0.2. Now, this step is pretty much the exact step that we do normally with the change. So if I were just to kind of write the change here in red, normally we would do minus x, right? Minus 4x and plus x. The deal here is we already know what x is. So x is 0.2, x is 0.2, and x is 0.2. We still have to take into account, obviously, the coefficients like normal. So again, instead of using x's, we already kind of know what x is. So in these cases, we typically just put the numbers in place for that. Any questions on that there? All right, so nobody gets confused. You can kind of cross that out there, but that's essentially what's going on there. And just like normal, we're just going to carry down here to our equilibrium. And we're going to assume that all of the copper is definitely going to get used up in this case because it is going to be limit reagent. Question? Yeah. No, it doesn't necessarily mean that. It just means really it's going to go to the right in this case. Yeah. Now we've got 1.2 minus 4 times 0.2. That's going to give us 0.4 molar, and we will have 0.2 molar. So the first assumption that we make in these type of problems is typically the metal should get used up completely because we're going to basically have the reaction go all the way, almost like in a one direction to the right. Now, you may be thinking to yourself, well, isn't the question how much copper 2 do we have at equilibrium? And if that's always the case, shouldn't always the answer be 0? And that would be awesome if that was always the case, but it's not. So the second part of this assumption is that although we are going to assume that everybody's going to the right, the second part is it is still a reversible reaction. So even though it is almost all the way going to the right, there is still going to be a little bit of it coming back in the other direction. So there's still going to be a little bit of it that's going to fall apart. So the second part of the assumption is there should still be a little bit of it coming back and falling apart, which means that when we calculate the concentration of the metal, it should be very small. So we should have a very, very small amount of the free metal still floating around in the solution. So what we do at this point is we actually go back here, and even though we zeroed out the metal, we now are going to call the metal X. And we're going to actually go back and solve for what the value of the copper is, the free copper floating around that solution. To do that, we're actually going to use our equilibrium expression to do that. So just like normal, we're going to put this in here and solve for X. So if we do that, we will end up with 0.2 going into our equilibrium expression divided by X, which is our copper concentration, ion concentration. We have 0.4, which is our ammonia. And again, we don't want to forget that we do need to also take it to the fourth power. And that's going to equal 5.0 times 10 to the 13. We're going to basically solve for X in this case, which is the copper concentration. And to do that, you're going to divide this to the other side. And then you're going to multiply this to the other side. And ultimately what happens is those two guys switch places, basically. So multiply the X to the other side and divide the 5 times 10 to the minus 10 to the 13, divide, and then multiply the X to the other side. And you will end up with 0.2 divided by 5.0 times 10 to the 13 times 0.4 to the fourth equals X, which is equal to our copper ion concentration in this case. So now that when we do it, we will end up with 0.2 divided by 5 to the 13 divided by 0.4 to the fourth. Bless you. That is going to give us a copper concentration. I'll write it right about there. of 1.6 times 10 to the minus 13 in this case. Yeah. Any questions on that there? Now, when we look at what we ended up with in this particular case, is the concentration of copper a large concentration or a small concentration? That is a fairly small concentration. It pretty much is 0 at this point, right? But there is still a smidge if you want to go out about 13 decimal places right there or so. You will have a little bit of copper. So what we see here is what we anticipate, that most of the copper or the metal does get tied up in the complex ion. The formation of complex ion is really favored in this case. As you see, pretty much it takes all of the metal and hooks it up with those ligands to make the complex ion. Very, very, very small amount of free metal is still floating around in solution. Any questions on that there? Now, by the way, if you get to this point and you calculate the copper concentration and it's a large number, you definitely screwed up somewhere. Yeah. So again, that's part of the assumption. You should end up with a small value for the metal. Any questions? All right. So I tried one. Why don't you try one here? All right. So why don't you try this one here? Let me rewrite these guys up a little higher, maybe easier to see. So we got silver plus S2O3 2 minus Ag S2O3 minus, and K1 is going to be 7.4 times 10 to the 8. And then we got this plus this guy here. And K2 3.9 times 10 to the 4. All right, so in this case, we want to calculate pretty much the concentration of everybody. And we're going to make a solution by mixing 150 milliliters of 1 times 10 to minus 3 molar silver nitrate with 200 milliliters of 5 molar Na2S2O3. We want to know what is basically everybody's concentration along the way. So give it a go, see what you come up with. Here, this is the stepwise fashion of what's happening. Again, you could add them together, get the overall reaction of what's going on, and see what you come up with. All right, so work on it for a little bit, and we'll talk about it. A little bit different than the first one. Here we are given a stepwise sort of formation of this complex ion. As I mentioned earlier, in this situation, you can add these steps together and get really the overall sort of reaction that's taking place. So if we did that and kind of added them together, this little sort of intermediate guy would cancel out, and we would be left with our silver plus we have 2 of the S2O3 2 minuses would come together basically and form our complex ion of this guy here. We could also, if we wanted to, get the Kf value for this by, again, since we added those together, we're going to multiply, not add, the 2 K values that were given to us for each of the steps. And that would get us, in this case, 7.4 to the 8 times 3.9 to the 4. And we'll call it 2.9 times 10 to the 13. First off, any questions on that part there? So now that we have sort of the overall reaction, we do want really the concentration of both the metal, the silver ion, and the concentration of the ligand, the S2O3 S2O3 2 minus in this case. And if we look, obviously here, the silver nitrate is our source of silver ion, and our sodium here is our source of our ligand, our S2O3 2 minus. We're obviously mixing these together, so we actually do want the concentration of each of those once they've been mixed together. So that is going to be like an M1 V1 equals M2 V2 situation. Here our total volume is 350 as we have 150 of one and we're mixing it with 200 of another. So we got 350 milliliters total. So if we want the concentration of silver that we kind of put together, we will do that. It will equal our molarity of our silver nitrate, 1 times 10 to the minus 3, times the volume we're using of it, 150 milliliters, divided by our total volume here. And again, a reminder, if we're using our dilution equation, we can't leave everything in milliliters. It's all good. And if we do that, 1 to the minus 3 times 150 divided by 350, gonna get us a 4.29 times 10 to the minus 4 molar. That is essentially our silver concentration as we mix them together. We also want to do the same thing for our ligand, our S2O32 minus. And again, we have 5 molar of it. And we're using 200 milliliters. And again, that's going to be the same total volume here of 350 milliliters. And that's going to get us here, not 2,000. Let's try 200, not 3,500 either. And that's going to give us a concentration of 2.86 molar. Any questions on that there? All right, now that we have the overall reaction and we have the concentrations of each of them, we could actually start getting to solving for some of this. And again, in this situation, we are looking for pretty much concentration of everybody. So there are multiple ways you could kind of get there. So let's just take a look at maybe an easy way or a good way. So if we take our overall reaction that we had, which again was our silver plus our 2 of our ligands there. Oops, 3 minus 3, 2 minus, right? That's a 3, 2 minus. Going to our silver here, S2O32, 3 minus. And we can do our ice table. So initially, we're going to use our concentration of our silver, which was 4.29 times 10 to the, what was that, minus 4. Minus 4. We're going to use our initial concentration here of our ligand and 0. Once again, we are going to make our assumption here that all of that silver should get used up. So again, the change is going to be our silver. And remember, when we come here, we still need to take the coefficient into account. That again is like minus 2x. So 2 times 4.29 times 10 to the minus 4 and plus 4.29 times 10 to the minus 4. That means when we reach equilibrium, we have none of that left over. Oh, come here. We got 2.86 minus 2 times 4.29 to the minus 4. Going to essentially still give us about 2.86. And we'll have 4.29 times 10 to the minus 4 molar. So doing this first ice table here with the overall reaction actually gives us 2 answers we're looking for. We now know that the concentration of S2O32 minus is going to be 2.86. We also know the concentration of our complex ion at the end will be 4.29 times 10 to the minus 4. So we kind of know this guy. We also know our ligand. At this point, we are looking for some other information. So we still need to find this guy's information, as we already got this guy. And we still need to find this guy's information. Now, at this point, there are really a couple ways you could do this. And I'm just going to kind of take the cross up there, maybe. There we go. Now, the way I'm going to find this guy's concentration is I'm actually going to use one of the steps there in the equilibrium process. And I could do that because I just solved for pretty much in that last table this concentration, and I know this concentration. And basically the only thing missing at this point is this guy's concentration. So because I have two of the three pieces of information there for my K2, I could actually just go back into the K2 step, and because they're all equilibrium, right? So they're all the same concentrations at equilibrium. And I can actually just use the K2 step of it to figure out the missing concentration. So if I do that, again, kind of coming back here and using the K2 step, I will write my equilibrium, which is my K2 equals 3.9 times 10 to the 4. And that equals the concentration of my complex ion divided by the concentration of that sort of intermediate that we're interested in, and my ligand here. And again, I have basically two of those three pieces of information. Now, the question that you may be having is, why am I not squaring this? And I'm not squaring this because I am not using the overall reaction. I am using the second step where there is no coefficient but one. So again, that's why we're not squaring it, because we're using the second step only, and there's only one of them in that case. So putting in our numbers here, this gives us 3.9 times 10 to the 4 is going to equal 4.29 times 10 to the minus 4 divided by our intermediate that we're looking for, concentration, and our S2, which is 2.86. Once again, if we rearrange it, these two guys will basically just switch places. And that's going to give us this intermediate concentration if we solve it by switching those two guys around. That's going to give us 4.29 to the minus 4 divided by 3.9 to the 4 when we switch it, and 2.86 divided by, going to give us a 3.8 times 10 to the minus 9 molar in this case. And again, basically switching these two guys. Yeah, we'll do that. Any questions on that there? At this point, I could also do a similar move because what I just solved for was that intermediate. And if I look back at the first step in the stepwise fashion here, I now have this guy's concentration that I just solved for. I still have this guy's concentration. Now I can use the first step and actually get silver's concentration if I choose to do so. And that's what I'm going to do here. I'm going to use step number 1 now to figure out silver's concentration since I have the other pieces of information. So looking at step number 1 here, are using K1. We're going to end up with K1 is 7.4 to the 8 is going to equal the concentration of our intermediate divided by the silver concentration and our ligand concentration. Once again, no squaring of the ligand because we're using step number 1, where once again, there is no coefficient there for step number 1 for that guy. Putting in our numbers, we're going to get what we got there. We got this guy we just solved for, which is 3.8 times 10 to the minus 9 divided by our silver concentration and our ligand, which is 2.86. Once again, these two guys are just going to switch places to solve for it. And that's going to give me a silver concentration that's going to be equal to 3.8 to the minus 9 divided by 7.4 to the 8 divided by 2.86. That is going to give me a silver concentration of 1.8 times 10 to the minus 18 molar. This does meet our normal assumption for a complex ion. The amount of silver here is super small, right? Which is what we would expect to happen, as the silver should be tied up in that complex ion. First off, any questions on those moves there? Now, to show you that you can approach this in a couple different ways, you could have, if you wanted to, went right after silver like we did in the previous problem after you did this first table. So you could have went after silver first by using this table and the combined K value we got there for it, which was this value, 2.9 times 10 to the 13. And just to show you, it will come out the same. We'll just take a look at that. So we're going to do the combined reaction here. And that's going to be our KF, which again is our 2.9 to the 13. It's going to equal our concentration, if we write our equilibrium expression for the overall reaction. Going to be our complex ion divided by everybody else. So our complex ion divided by our silver and our S2O32 minus. Now here I do need to square it because now I'm going to be using the overall equation in this case, and there is a 2 there, so I do need to square it. I again have all my numbers there from the first table, so pop in those numbers in. We're going to get 2.9 times 10 to the 13 is equal to 4.29 times 10 to the minus 4 divided by our silver concentration and our 2.86 that is squared in this case. Should be 4, yep. And again, to rearrange this, these two guys are going to switch places, which will give us silver is equal to 4.29 times 10 to the minus 4 divided by 2.9 times 10 to the 13 and our 2.86 squared. And if we do that, we hopefully should end up with the same silver concentration we had a second ago. And if we do that there just to verify, we end up with basically 1.8 times 10 to the minus 18 molar in this case. And obviously, as you can see there, that is exactly what we got here when we use the individual steps. So you can use the overall one. At this point, if you did go this route, you would have silver, and you could use step number 1 to figure out the intermediate if you wanted to. You go back to the first step and you can figure out the intermediate at that point. So there are a couple different ways you could do it. And you can see they all come out kind of the same in this case. Any questions on that there? So again, if you took this route, you'd again probably go back at that point and come back here, because now you would have this and you would have this. You could then solve for the intermediate and get everything that you would need at that point. Any questions on this one here? Yeah. All right. Take a look at one last one here and calculate the molar solubility of silver chloride in 1 molar ammonia. So in this case, we have a couple different equilibriums happening. We have a KSP equilibrium there, and that's our silver chloride breaking apart into our silver ion and our chloride ion. And we also have a KF equilibrium, a complex ion equilibrium that's happening where the silver is going to react with the ammonia and make this complex ion. So once again, we do have 2 equilibrium reactions. Is it okay I add them together even though they're different Ks? The answer is yeah, they're all K values. It doesn't really matter what the little letter on the bottom is. So you could add all these together. And if I add these 2 reactions together, it does give us really the overall reaction that's sort of taking place. In this case, our silver is going away. And we're left with our silver chloride plus some ammonia and it is going to make this complex ion and some chloride ion in this case. By the way, just like before, we could get a K value for this by multiplying the KSP times the KF in this case. And if we do that, we will end up with 1.6 to the minus 10 times 1.5 to the 7, it looks like. That's going to give us a 2.4 times 10 to the minus 3. By the way, this reaction perhaps looks familiar to you because you actually did it. That is the very ending step of group 1 qualitative analysis when you added the ammonia to your solid and it disappeared. And then perhaps you added some nitric acid at the end and it came back to confirm silver. All right, so what we're really looking for here is the molar solubility of silver chloride and ammonia, which is what our overall reaction is really looking at. So remember that molar solubility is really more of a KSP type problem, and this is really what we have going on here. We're going to approach this more as a KSP problem since we're looking for that molar solubility. So if we take our overall reaction here, and again, add it together, going to give us our silver chloride and our couple of these guys here. And again, making our complex ion and our chloride. All right, so we're going to do an ice table here, and really the only thing we're told is, we dumped in 1 molar ammonia, basically. So we actually will have an initial concentration of ammonia over here, which is 1 molar. We don't know anything about this guy, and we definitely don't know anything about this guy. Even though we are interested in the molar solubility of silver chloride, it is still a solid, which means it's not going to really participate in anything. So I'm just going to leave it empty for now and not put any numbers there since it's a solid. Change in this case is going to be minus 2x plus, you could use S since we're doing molar solubility. We'll use the little S there. So let's use... Remember that we use S here for molar solubility, plus S, and plus S here. That means at equilibrium, we'll end up with 1 minus 2S, S, and S in this case. Any questions on that so far? Like normal, we're going to do our equilibrium expression, which in this case is again our products over our reactants. And again here, not including the silver chloride since it's a solid. And we'll use our combined K value we got on the previous slide there. Looks like it's 2.4 to the minus 3. Putting in our numbers here, we're going to get basically S squared divided by 1 minus 2S squared is equal to 2.4 times 10 to the minus 3. That looks like a nice little perfect square situation happening there. And that's going to get me a S divided by 1 minus S is equal to, should not forget to take the square root of that side there. Going to get me 4 point, we'll call it 90 times 10 to the minus 2. We're going to multiply this to the other side, and that will get me S is equal to 4.90 times 10 to the minus 2 minus 4.90 times 10 to the minus 2S. Combining my S's, I'm going to add this back to the other side. That's going to get me 1 plus that. Going to get me something like 1.049S equals 4.90 times 10 to the minus 2. We're going to divide now to figure out S. And that's going to get me, call it S is equal to 4.7 times 10 to the minus 2. Remember, that is the molar solubility here of silver chloride. If we take silver's molar mass there, was that 107.9 perhaps, and 35.45, it's like 143.35. So if we take this 4.7 times 10 to the minus 2 moles per liter and times it by the molar mass of silver chloride, that is going to give us our solubility in grams per mole. And that's going to look, our grams per liter, that's going to look like 6.74 grams per liter. It is soluble. Yeah. Question on that one there. Now, if you remember, probably not, if we look at silver chloride in water, its solubility is molar solubility 0.00000126. And if we times that by 143.35 grams per mole, that is a solubility in water for silver chloride of 0.0018 grams per liter. So that is the solubility of silver chloride in water. Solubility in ammonia is 6.7. Which one is it more soluble in? It is way more soluble in ammonia, right? You could get about 6.7 grams of it to dissolve in a liter of water. In water without ammonia, you could only get 0.002 grams of it to dissolve, right? Not very soluble at all. This is why, if you remember when you did that step on group 1, you had your silver chloride in the solid, and the ammonia was able to basically rip it out of the solid and make this complex ion. And that is because the Kf or the formation of a complex ion is much favored than keeping it in a solid. And that's why you're able to kind of remove it from its solid state and make this complex ion that can float around as well. By the way, in this experiment, right, you did that, and then you added nitric acid and you saw the solid come back. The reason for that is when you add the nitric acid, the ammonia goes away, it gets protonated, and now the silver's free again, and it's able to find our chloride that's still there and remake the silver chloride, which is why you saw the solid come back at the end of that experiment, that white solid reappear at the end of group 1. Any questions on that there? All right, that is chapter 15. Yeah, I could just flip the page there and found the solubility. Yeah. So here's a table, and you have a similar one in your book. And again, one of the differences between KF, obviously, and KSP is in KF, we have very, very big K values. As you can see, we got some are like to 33, 43. So these are really, really big values of K. That means that products are always going to be favored in this case. The formation of that complex ion is definitely going to be favored. And that's really in contrast to what we see with KSP, where we have really, really small equilibrium values, and our reactants are favored, which means it's favored for it to stay together and not break apart into ions and keep the solid together. Any questions on any of that there?